Hello, and welcome back. Today, I want to look at the design process and steps to take when you need a current Balun. I needed this transformer for a project I'm working on, and rather than doing the lazy thing of just taking a random core and throwing some wires on it, I decided to do things properly. Or at least try. So if you're curious, then keep watching. Before looking at the transformer, let's first analyze the problem and define some parameters. So I need to take a 50 ohm unbalanced line carrying up to 5 watts and convert it to 200 ohms balanced. This should not be all that difficult, so I decided to use a couple of guanella transformers to do this. So 2 identical transformers will be needed. Because of the way in which these are connected, the 1-to-1 transformers will see the same impedance on both sides, which in this case is 100 ohms. 2 times 100 ohms in parallel form the 50 ohms of the input, and 200 ohms in series form the 200 ohms of the output. Since this is quite a common impedance value, we can use proper 100 ohm transmission line and just make a transmission line transformer. This should minimize losses caused by impedance mismatches. Next, since the input power is going equally through each transformer, it ends up getting divided, so each branch will only see half, so 2.5 watts. Considering the system impedance, this translates to an RMS current of 316 milliamps total, which divided up is 158 milliamps through each of the transformers. The final parameters that we need to keep in mind have to do with the use case. The Balun is part of a design that will operate in the upper part of the HF bands, so operating frequency can be defined as 15 to 30 MHz. And since the current Balun is more or less a common mode choke, the main operating utility that it presents is that it blocks common mode current by providing a high common mode impedance value. So we can set our impedance target to be about 15 times the transmission line value, so 1.5 kilo ohms. And well, this should be enough to get us going. With the basic parameters out of the way, it's time to look at the actual core. Since we're essentially building a common mode choke, our goal is to get a lot of common mode impedance, while minimizing losses. The precise impedance value is not all that critical, so we can use a magnetic core. And the higher its permeability is, the fewer turns we need, and thus the lower the losses will be. While I do have quite a few cores lying around, for most of these I don't really know exactly what they're made of. I can measure the inductance coefficient, but that does not tell me the full story. So I decided to just choose between the cores where I do know the exact material, and more importantly, where I also have a complex permeability graph. The thing that I'm looking for is a core that has either real or imaginary permeability. I don't really need the inductance, just the impedance, but this needs to occur in the area of interest, the 15 to 30 MHz range. After looking around a bit, I decided to go with a Type 52 material-based core. This specific material has relatively large permeability at the 30 MHz mark, the sum of the real and imaginary being around 200. But other than this, I also looked at other materials like the Type 43. This is presenting similar properties at our frequencies of interest, though it's a bit more resistive than inductive. And we also get a slightly higher permeability of around 300. So this material should be better. But it's worth noting that I actually do have a few Type 52 material cores around. So this also made me lean towards this material, even if it's not the best for our use case. Now, with the material decided, next the actual core dimension is usually determined based on the flux handling capabilities. For a common mode choke, that is more or less negligible, since the common mode current is supposed to be very small, so our main concern today will be to actually get the desired impedance without having too many turns. More turns means more loss, and also more parallel capacitance, none of which is something desired. So next, I use the AL values as well as the reference permeabilities for all 3 core sizes and well, for the two types of material, and calculated the necessary number of turns for the two extreme frequencies, so that we get the desired impedance, using the formula on the left side. So for type 52 material, we would need about 12.0 turns for the smallest core, and around 8 turns for the largest one. And for the middle-sized core, we need 11. Now, in all cases, you do need to round up just to make sure that you have enough turns to ensure the minimum impedance, and you need to select the largest value from the pair. So, based on all of these numbers, I decided to go for the middle FT82 sized core. The core isn't all that large, and the turns number isn't unrealistic either, especially when you remember that the wire will be quite a thick, twisted pair. What I mean is that you don't just want a small number of turns, they should also fit without overlapping. Now, if I would have gone for a type 43 material core, then the numbers would have been a bit smaller. So for the same sized core, I would have used only 9 turns. But anyway, this is the number of turns I will be going with. For the actual wire, there are two things to keep in mind. First, it needs to be able to carry the useful current, 360 milliamps in our case, which is not all that much, so nothing really special is needed. But the other thing is that we want an 100 ohm differential transmission line. This usually needs a bit of design. However, for today, I decided to just use some cable I already had lying around. Ethernet cable. Now, while I don't have the datasheet for my exact cable, I took this generic Cat5 cable as reference. So this datasheet highlights that the impedance of this type of cable is 100 ohms, plus minus 15%, and the attenuation that we should expect is around 1.8 decibels per 10 meters at 31 megahertz. Or, if we go for shorter cable lengths, say 1 meter, then this is 0.18 decibels. So, based on the core sizes, we should use less than 1 meter for both transformers. In other words, the cable loss should not be a major issue. Now, you can of course use cables which ensure much tighter impedance control than this one and lower loss, based on your needs of course, but for today, a Cat5 type of cable should do. So finally, this is what the transformers I built look like. 11 turns of twisted pair from a piece of Ethernet cable wound on a FT82-52 core. I also made this small frame thing and set everything in place with some hot glue. Because this thing is handmade and, well, my patience is limited, the turns are not equally spaced, though ideally they should be. And the wire should not leave gaps towards the core. But this will be good enough for now. But before using these in an actual device, it's first important to check what the achieved transformer parameters actually are. So, first things first, what is the common mode impedance of the transformer? For this, I soldered the first one to a SMA connector, so each of the two windings were interconnected, and therefore the transformer behaves like a single inductor. This is then connected to the first port of the VNA. Using this setup, we can see that the impedance is frequency dependent, it rises with frequency, and the minimum that we get is at 15 MHz, and it's 1.75 kiloohms. So we are clearly above our 1.5 kiloohm target. We can take this measurement one step further and decompose the absolute impedance into resistance and inductance, and see just how the two values add up. So at both frequencies, more than half of the impedance is found in the resistance. This is quite a good thing, since it means we are less likely to get oscillations. But on the other hand, any common mode current will be converted to heat. Anyway, I made the same setup for the other core as well, just to see how similar the two transformers actually are. And while going through the measurements, with the second transformer, the impedance is a bit lower, We are well within the 25% tolerance of the score, so this value difference should not be all that surprising. But more importantly, we are still above our target value with this transformer as well. Again, looking at where the impedance is coming from, we see that this second core is slightly more reactive. There is a bit more inductance and a bit less resistance. Anyway, next thing to look at is the insertion loss. How much signal are we expecting to lose when passing through the two cores? Since the transformers are built as 100-ohm transmission lines, by placing them in parallel, you essentially get a 50-ohm line. So this is what I will be measuring. I connected one side to the first port of the VNA and the other to the second port. And with this setup, we should be able to observe how much signal gets lost when injected through the transformer assembly. Looking at the results, while the measurement is quite noisy, the values are still very small. We are losing somewhere in the 0.03 to 0.04 decibels. So this means that using this transformer will create minimal issues, especially when running QRP levels of power. Finally, I wanted to look at the return loss to observe just how 50 ohms is my 50 ohm setup. For this, I connected one side of the transformer pair to the VNA, so to the first port, and the other is connected to a 50 ohm termination. In an ideal world, the S11 parameter would be -infinity, but that's just wishful thinking. With the practical cores, we are somewhere in the -29 to -23 decibels. Not perfect, but still very respectable values. While this may or may not make all that much sense to you, another way of looking at this result is by checking the SWR. The same measurement goes from 1.07 up to 1.14. Not ideal, but not all that bad either. After running some academic verifications, test instruments, and close to ideal use cases, it was time to observe something a bit more close to life. What if I connect a realistic signal source and a somewhat realistic load? So the actual use case I have for the final Balun is passing signal from my low power transceiver to an antenna. So the experiment I wanted to perform is to connect one side of the transformer to the transceiver and the other to a dummy load, and then just hit transmit and see if anything heats up. The transformer is still configured as a 1-to-1 50 ohm setup from before, and as load I'm using an attenuator. So this way I can also monitor the signal at the output just to check what is actually passing through the system. For this setup, I ended up using almost half of all of my adapters and connectors that I had, but at least it should work. So after connecting everything and setting the transceiver to the 10-meter band, I just hit transmit, verified that there is a continuous signal passing through, and waited. After a bit of time, I took the thermal camera to check things, and sure enough, the load was indeed heating up, even if just by a little. But more importantly, the Balun was the same as the ambient. Waiting a bit didn't really change things. So it's safe to say that the insertion loss is indeed negligible, at least with this sort of setup. So this should be quite a good transformer to be used in a future project. In the end, while there will always be a better way, design is all about compromise. What is economically feasible, what are the materials available, and what corners can be cut while still achieving the end goal. No design is perfect, it just needs to be good enough to satisfy the initial requirements. Better than that is not really mandatory. So the transformer I designed today, I will use in a future video. Hopefully it performs as good as the experiments showed. So with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.